Thank you, Josh, and thank you to the Josh and James and various people for inviting me to come here. It's been not the sort of things I usually think about, but it's been fun. And yeah, so this will be definitely a little bit different. And I think parts of it you'll probably find very elementary / pedantic, and parts of it you'll find very confusing. Hopefully more of the former than the latter, but we'll just sort of see how it goes. Well, my training is as a differential geometer. I'm actually more of a symplectic geometer and geometric probabilist and various other things these days. And I actually haven't, I'm going to tell you about curvature tensors, but I haven't actually had to get my hands on a curvature tensor in a while. So, but nonetheless, and for me, all tensors are either matrices or differential forms in my actual life. So that's my perspective on things. But I'm happy to be more broad-minded about it. So I just briefly want to mention, so Harrison is a postdoc at CSU, and I'm going to mention, I hesitate to even call it a theorem, but a result with Harrison, which we're not sure if anybody knew this or not and whether anybody cares or not, but I think it's kind of interesting. And then also Colin, who is right there, he gave a talk in the graduate seminar at CSU on tensors in the fall as they relate to geometry, and this is to some extent inspired / ripped off from his talk. And I will not be at the Pingree Park next week, but he will, and so if you're interested in questions about tensors and geometry and stuff like that, of course you're welcome to talk to me or email me, but you should also talk to Colin because he is very well-rounded when it comes to geometric ideas. So I encourage you to seek him out. Okay, so differential geometry. What's the basic idea? The basic idea is we want to do multivariable calculus on spaces that are not Rn, right? That's the basic problem. And why is this hard, right? You say, okay, well, but look, in multivariable calculus we talked about, surfaces and we did stuff and curvature and blah, blah, blah. Like, why is there anything new to think about? And the basic answer is because spaces that you care about don't necessarily come embedded in any Rn. Okay, there are various embedding theorems that tell you that yes, if you want to embed your space into some Euclidean space of sufficiently high dimension, you can do it, but that's often not very productive or interesting or useful because it may well be the case that the space that you have has some very natural coordinate system that you'd really like to work in that is sort of intrinsic to that space, but sort of completely falls apart if you try to embed that space into some Euclidean space. So we want to work intrinsically in the spaces that we're thinking about. And for me, spaces, could be spaces of conformations of a protein, like the different possible configurations of a protein, or a space of linkages. So you have some mechanical linkage. You want to know what are all the possible conformations of this mechanical linkage. Or you are doing signal processing and you say, well, I'm modeling my detectors as just taking dot products of some collection of vectors, and I'm looking at sort of the conformation space of all possible vectors that have certain properties or whatever. And so these spaces are maybe given to you in some fairly natural way, and they turn out to be nonlinear spaces. And again, there is some embedding theorem that tells you can embed them in some high dimension Euclidean space, but at the cost, of, squaring the dimension or something like that. Okay, so we want to do calculus. We want to, think about things like compute rates of change, or compute integrals, or compute lengths of curves, which is just integrating, the norm of the vector along the curve or whatever. And the basic problem in differential geometry is, okay, you want to compute a directional derivative. So you have some difference quotient. So you say, okay, well, I have some vector field. I want to look at the vector field at this point, the vector field at this point, and sort of see how different they are and do some difference quotient thing and define a directional derivative, right? Okay, in Euclidean space, this is no problem. You have a vector at this point, vector at this point. You do the usual trick and you say, oh, well, all vectors are secretly based at the origin, and so these are, I can just take this vector minus this vector and everything's fine, right? Well, it doesn't work. in non-Euclidean spaces, right? You say, okay, I have this vector at this point, and this vector at this point, and okay, like we say our manifold has some tangent space at this point that this vector lives in, and has some tangent space at this point that this vector lives in, but these two tangent spaces are completely different vector spaces. You can't do u minus v. It's nonsensical, right? They live in different universes. That's the basic problem that leads to sort of all of the interesting and annoying aspects of differential geometry. And so somehow if you want to define a difference quotient, a directional derivative or a Lie derivative or whatever derivative you want to talk about, you have to figure out some way of getting this vector into this tangent space so that then you can take u minus v, right? And really what you're doing in Euclidean space is you're saying, okay, well I have this vector at this point, this vector at this point, I'm parallel transporting over to here and then comparing them, right? And so one of the tricks that you can do in differential geometry is parallel transport. Well, how do you do that? You have to know what it means for things to be parallel. And then that's sort of where things get started. So this is really the basic problem. All right, so what's a vector field, right? So we kind of know what it means. It's like, okay, you have some tangent vector at each point in your space, right? That's a vector field. And maybe you want to add some regularity condition. You say, well, I would like this vector field to sort of vary smoothly. As I change my base point, I want this vector to vary in some sort of smooth or at least differentiable or at least continuous kind of a way. How do you encode that, right? Not so easy. This is what we've come up with. We define this thing called the tangent bundle. Okay, what's the tangent bundle? Well, at each point in my manifold, I have a tangent space. And I haven't really told you how to define the tangent space. I'll say more about that in a minute. But I have some tangent space, which is some vector space. So each point has a vector space. So if you like, I have this sort of family of vector spaces which are parametrized by the points in the manifold. And I can just mush these things all together as a giant disjoint union and get a set, which turns out to be a space, which actually turns out to be a differentiable manifold of essentially the same regularity as you assume in your base manifold. So this thing is some manifold of twice the dimension of this thing, right? So here this has some dimension n. Well, so my parameter space is n-dimensional. Each of these vector spaces is also n-dimensional, and so you get some 2 n-dimensional thing up here, right? And then this is what's called a vector bundle, which just means that there's some projection map, which is sensible, and it turns out to be a smooth manifold, and et cetera, et cetera. So I have a smooth manifold here, I have a smooth manifold here, and then formally we define a vector field to be a map that goes the other way in such a way that if you go up and then down, you end up back where you started. So that's what's called a section of a vector bundle, is a map that goes up so that when you go up and then you project, you end up back where you started. Okay, it sounds abstract, and what's the reason for doing this? Well, this is a manifold, differential geometry nonsense tells you what it means to say that a map from a manifold to a manifold is a smooth map. And so I can say what it means for this map to be a smooth map, and if I require it, then implicitly what I'm requiring is that, well, if I change my base point a little bit, I'm changing my tangent vector in some differentiable way. So this, of course, was not the original definition of a vector field, but it's the definition we arrived at after 100 years, when we realized, oh crap, instead of writing down, 8 pages of sort of local coordinate, equations, we can just say this, and then it's equivalent to those 8 pages of local coordinate calculations, right? Yes?
This is equivalent to what we learned in school about charts analysis.
Yes, yep. Yeah, so that is all hiding behind the covers if you really want to get into it. And indeed, you say, okay, well, if I have some coordinate chart on here, I get some induced coordinate chart on here, and if I work in local coordinates, I can convince myself that all of the coefficient functions of local coordinates are in fact smooth functions, follows immediately from this definition, yes. Okay, but now, Okay, so here's an example of a vector field, right? So this definition, I say, okay, I have a smooth section of this vector bundle, and you say, I don't understand vector bundles, and I blah, blah, blah. What does it mean? All it means is I'm choosing a tangent vector at each point, right? Because I have this map, a map from M to Tm, so every input is a point in the space, and my output is some element of the tangent space. That's what this condition says, is that, well, if I input a point x, the thing that I get up here has to be in the tangent space to x, not the tangent space to some other point over there, right? Because if I map to some other point and then project it down, I end up at a different point than I started. So all this is saying is I'm choosing a tangent vector at each point, and then the smooth business is telling me that it's varying in a smooth way, which is equivalent to saying in any local coordinate system, the coordinate functions are smooth functions. Okay, so fine. Two comments for you algebra-oriented people is that, first of all, the collection of all vector fields on a manifold forms a Lie algebra. I will say more about that in just a second. You can think of this thing as a module over the algebra of smooth functions on the manifold. All right, so that is a vector field. And the point is, I'm defining it as a section of some vector bundle. That's sort of the takeaway you should get from this. And whatever those words exactly mean, it just means I'm choosing a thing in the vector space at each point in some smoothly varying kind of a way. Okay, so let me say briefly, it turns out if your space is not actually embedded in Euclidean space, it's not so clear what you mean by a tangent vector at a point, right? You have to, if you have any experience with thinking about projective space or, some other weirdo nonlinear space that doesn't have a completely natural embedding into Euclidean space, it's not so clear what you mean. Like if you have actually, all my pictures are of the sphere because it's easy to draw. If you have the sphere in R3, then it's clear what you mean by the tangent space. It's like, well, it's the plane which sort of touches. It's this plane that touches at this point and is sort of tangent in some appropriate sense. But if you think of this space, this sphere, as sort of not living inside of anything, like it is the universe, then then what do you mean a tangent vector at a point? Like you can't talk about, oh, it's the hyperplane in the ambient space that sort of touches it. There's no ambient space. There's nothing. So you need some intrinsic definition of what it means to be a tangent vector. And here's roughly, so I have a point and a manifold, and I'm supposed to have some tangent vector. What do I mean by this tangent vector? Well, here's what I mean. If I have a curve that passes through the point, well, what is a curve? It's just a smooth map from an interval into the manifold, and I'm, say, requiring that the interval is from minus epsilon to epsilon, and that the image of 0 is the point that I'm talking about, right? Then what's a tangent vector? Well, it's just, the tangent vector to the point. It's just sort of the derivative of this curve at this point. Okay, but what does that really mean? Like I can draw arrows and whatever. So here's what it really means. Okay, so I guess I wrote this as saying a vector field is a differential operator. In some sense, a tangent vector is like a differential operator at a point or in the neighborhood of a point. And so what that really means is like, okay, if I have some smooth function or at least smooth in a neighborhood of this point, then what this tangent vector actually does is it's a directional derivative operator. And so the sort of genius insight was that, okay, we don't know what tangent vectors mean in general, but a vector field in, say, Rn is morally equivalent to the directional derivative operator induced by that vector field. And you can make sense of a directional derivative operator in much more general contexts. And so, Okay, so this is supposed to be so I have a function, I hit it with a vector field, that's supposed to be some new function. What is the value of that new function at this point? Well, it's this, so I say, okay, well I have, gamma is a map from an interval into my manifold, and then f is a map from the manifold to R. So if I do gamma and then f, I have a map from an interval to R, right? Well, I damn sure know how to take that derivative, right? That's calc 1. And so that's the value of this function, xf, at the point x. And I can do it at any other point, and this all kind of works out. And you have to convince yourself that it didn't really matter which, gamma I chose, and et cetera, et cetera. And if you know any, algebraic geometry, you know that you define the tangent spaces, the collection of derivations, modulo, blah, 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 right? If you don't understand those words, don't worry about it. It's this, basically, in some slightly more general context. So that's what a tangent vector actually is, and the tangent space is just the collection of all tangent vectors at that point. So all things of the form gamma prime of 0 for some gamma passing through the point. Okay, so I mentioned briefly there's a Lie bracket. So, okay, what's the Lie bracket? Well, so if I have two vector fields, I take their Lie bracket. That's supposed to be some new vector field. Okay, again, a vector field is a differential operator, so I can say what this vector field is by saying what the differential operator is, which means saying what it does to an arbitrary function. And so what does this operator do to this function? Well, first I differentiate f in the y direction, and then I differentiate in the x direction. That gives me, something. And then I do it the other way around, and that's my Lie bracket. Yes?
So 0 means it's flat there.
Yeah. Yeah.
Does that have the full characterization of flat?
Almost. So, yeah, not, yeah. And so in particular, if you have a local coordinate chart, so if you work in local coordinates, you're saying, okay, I identified some tiny patch of this manifold with some open set in Rn, and then I'm taking sort of the coordinate directional derivatives in Rn, and mixed partials commute, right? So this is dead zero like on Rn, and then but in general, if you have curvature, it's not going to be zero. And I'll say more about how we define curvature, but it's related to this. All right, before I give you sort of the formal definition of what differential geometers mean by a tensor, let me talk about one-forms. So this is sort of the dual picture of what I just said about vector fields, right? So at each point I have a tangent space. Well, I can think it's dual, right? And that's my cotangent space. And then I can play the same trick. I just mush them all together into a single space, and I get some vector bundle. So that's called the cotangent bundle. So I have, this vector space at each point, and then I have this projection operator that tells you what point you're based at. And then a one form is a smooth section of this thing. So it's just again, at each point you assign a covector based at that point. And so the example to have in mind is I have a function on a manifold, and I can have the differential. Okay, think like Jacobian of a scalar valued function on R3 or something, and that's basically what this thing is. And that's a one form because what does it do? It eats a tangent vector at each point and spits out a number. And so if I feed in a vector field, I eat a tangent vector at each point and spit out a number, but of course that number can change depending on the point, so it eats a vector field and spits out a function. All right, so, and if you like, this is like the dot product with the gradient. And if you have a situation where you think you know what that means. All right, so tensor bundles, right? So I'm only claiming this is the way that differential geometers think about these things. I'm not claiming this is the right way to think about these things. So I have a vector space V, and I define the tensor space TPQ to be the collection of multilinear maps from P copies of V dual and Q copies of V in R, the base field. Yeah. So I'm depending very heavily on finite dimensional at all points in this talk. In fact, Yeah, so the idea is that you think of something that maps V dual to R, and of course that's an element of V double dual, but I'm thinking of it as just an element of V, because, and how do I go from V to V double dual? Well, in the usual way, the vector operating on a linear functional is the value of the linear functional on the vector. So, yeah, everything I'm saying is like totally bogus in infinite dimensions, or mostly bogus probably. All right, so if V is the tangent space at a point, right? Well, this tensor space is some vector space based at that point. And I play exactly the same game. I say, okay, well, I have, the tangent space, I have the tensor space over this tangent space at each point, and then I take the union over all points, and that gives me some giganto vector bundle.
Implicitly, aren't there isomorphisms between every txm for every x? So they're not really the same.
Yeah, so the question was, implicitly aren't there isomorphisms between all these things? Yes, these are all, real vector spaces of the same dimensions. So they're all abstractly isomorphic. And if you live in the same coordinate chart, there's maybe even sort of a semi-natural way to realize that isomorphism. But yeah, they're abstractly isomorphic, but you don't necessarily want to say that they're the same. Does that make sense?
But there's no natural reason that a Tx will have some basis that you're using for your dual that the Ty will use to have a basis.
So yeah, so the question is like if you have some basis at point X for this space and you have some other point Y, is there some compatible basis? And the answer is maybe. Like if the 2 points live in the same, coordinate chart, and going back to the definition of a manifold, okay, well, what's a manifold? Well, like, it's some space, and you have this collection of things called coordinate charts, which are maps from sort of open sets inside the same Euclidean space into the manifold that cover the manifold, and the transition maps are smooth, and blah, blah, blah. So if you're in the same coordinate chart, then you can sort of, push forward or pull back, depending on which way your coordinate chart maps go, the sort of coordinates on Rn, and get sort of compatible coordinates at these 2 points. But, if you're very far away, there's no particular reason to believe that there's any compatible, really, thing. If your manifold's orientable, then you can say, well, they're sort of in the same orientation class or something. But it's, this is sort of the devil of the details of differential geometry, is that, like, if you actually want to do a computation, you almost always have to do your computation in local coordinates. But you don't want to do any definitions or theorems in local coordinates, because then you have no idea whether whatever you were doing depended on the coordinates. So, yeah, it's kind of a pain. Okay, so for each P and Q, you get some bundle, some vector bundle, and then again, I didn't actually, okay, what did I want to say? Oh, right. I can also think of this, if you don't like this way of thinking about it, remember I said, well, the tangent bundle was like C infinity M module. The cotangent bundle is also some C infinity M module. So I could take a tensor of tangent bundles and cotangent bundles, as C infinity M modules, and I would get the same thing, if you prefer to think in that language. I never actually gave it, did I? Oh, no, I'm doing it on the next slide, sorry. This is just examples of tensor bundles. So if I take 0, 0 tensors, right? I should have also said, like, the way that I tend to think about this is like, okay, well, what's a tensor? It like eats a covector or some collection of vectors and covectors and spits out a number, right? So this is something that eats 0 covectors and 0 vectors and spits out a number, right? So that's just a function. If I eat 1 covector and 0 vectors, while I'm sort of, you know, doing this double dual trick, I'm just talking about a vector field, or a tangent vector. And the other way around for cotangent things. So these simple tensor bundles are sort of familiar things. And so a tensor field is, again, I've now done this 3 times, right? I had a vector bundle. I define a whatever field to be a section, a smooth section of that bundle, right? So same thing here. And so formally, you should really call these things PQ tensor fields. Almost always, this just gets called a PQ tensor because people are lazy, right? And again, it really is in some sense like an actual tensor, not a tensor field. If you're thinking this is a tensor product over this, you know, C infinity M, but it tends to be not how people really think about it, I guess. But yeah, so then the idea is like, well, what's a PQ tensor? Well, it's a thing which at each point eats PQ covectors and Q vectors and spits out a number in some multilinear way. So again, functions, vector fields, one forms, these are examples of, you know, a 0, 0 tensor, a 1, 0 tensor, and a 0, 1 tensor. Okay, important example is a Riemannian metric. Sometimes also called the metric tensor, which is a positive definite symmetric 0, 2 tensor field. Okay, well, positive definite symmetric, this is saying at each point, I eat a pair of vectors and spit out a number. And it's positive definite, meaning that if I put the same vector in both slots, I get a non-negative number. It's symmetric, so meaning if I swap which ones go where, I get the same thing. I guess I should have said non-degenerate too. But anyway, so the point is, at each point, oh, positive, yeah, sorry. Right, I said positive definite. I had in my head positive semi-definite, but yeah. So, right. At each point, you get an inner product on the tangent space, because what's an inner product? Well, it's a positive definite thing that eats a pair of vectors and spits out a number, right? So, you know, again, so a tensor field is a section, so you're saying if I input a point, I output an element to this tensor space. Well, at each point, you know, an element of the 0, 2 tensor space is an inner product. And so I'm getting an inner product on each tangent space, and it varies in some sense smoothly as I change my base point. I'm just showing you notation so that if you ever encounter these things, you aren't completely scared. Because I still get scared, and I've been looking at these things for a long time. So we often write, you know, a metric as like some coefficients times dxi tensor dxj, where these are sort of, you know, dxi, you know, sends xi to 1 and xj to 0 if j is not equal to I, and so on and so forth. And then I think we adopted from physics this annoying convention of doing the Einstein summation convention, where you drop the sum, and if you see repeated indices, you sum over those repeated indices. And then there's this really old notation where ds is supposed to be like the length element. Like if you're doing like line integrals, you have like you know, an arc length element. And so it's ds squared is gij dxi dxj. Again, this is just notation. And then sometimes you'll see your g just written like this, like you just see gij. And that actually means like the full tensor, not like the particular coefficient, but such is life, right? Yes?
I sometimes see a wedge in the tensor product. Is that interchangeable, or is that a different set?
For metrics, I doubt
I
it.
see it in these calculations, and they're just, it's not related to this.
Well, so I will talk about, you'll see wedges very soon. But not in the context of a metric, because a metric is a symmetric tensor, where a wedge is an alternating tensor. Yeah, it's not to say nobody ever does it, but it's a bad idea to do it in this context. But okay, so for example, right, ds squared is dx squared plus dy squared on R2 is just the standard dot product, right? Because what are you doing? So dx squared is really saying dx tensor dx, right? And so what is that going to do? Well, it's going to multiply, you know, so dx squared, so again, because vector fields are really differential operators, we tend to write them in this form where it's like, you know, the direction in sort of the x direction, or the derivative in the y direction. So this just means, you know, A in the x direction and B in the y direction. So I could also write this as AE1 plus BE2. But this is the notation that one often sees. And so the dx squared is really dx tensor dx. And so it looks through here and it says, well, where do I see a d by dx? Well, there's a d by dx, there's a d by dx. So the first dx grabs this guy, and the second dx grabs this guy, and so you get a times c, right? And then you also have dy tensor dy, and so the first dy sees this one, and the second dy sees this one, and then you get this. Okay. And of course, this is just the dot product of the vector AB with the vector CB. All right, here's a different Riemannian metric. So now I'm taking just the upper half plane. So the y coordinate is supposed to be positive, and I'm defining, okay, well, this is, again, this is really just telling me like what the inner products of some basis vectors are. And so what it's saying is like, well, if I got, an E1 and E1, well, their dot product would be, 1 over y squared, where y is, xy is the point where I'm at. And likewise, in E2 and in E2 would pick up a 1 over y squared. So you see that, here, you have the same thing no matter where you are. Here, where you are, you get a different inner product, right? And you have this weirdo sort of weight of 1 over y squared. And so this turns out to be the sort of standard metric on this upper half space model of the hyperbolic plane. And so on the hyperbolic plane, your geodesics are either vertical straight lines, right, or semicircles that intersect the x-axis perpendicularly, right? So these are all geodesics. And yeah, so that's what's going on there. Did I want to say anything else about this? Yeah, so the point, of course, is that like, if you think about distances, which I'll talk about in just a second, like as you travel in this direction at constant speed, you can never actually reach this point because it's sort of infinitely far away because of this 1 over y squared term. So you have this sort of whole, line plus one extra point at infinity where, you can go out and so this is what's called the circle at infinity or the sphere at infinity for hyperbolic space. And so the point is, like, if you have a Riemannian metric, you know how to compute lengths of curves, right? So if I have a curve, smooth curve, and I have a Riemannian metric, then okay, what's the length of a curve, right? Well, it's the norm of the tangent vector to the curve at each point integrated over the curve, right? So that's just this, right? So, right, the dot product of gamma prime with gamma prime, take the square root, that's what you would mean by the norm. So that tells you the length of any curve, and then you say, okay, well, what's the distance between point x and point y? We'll take all possible curves and just find the shortest one, or the shortest distance. So that's... So a Riemannian manifold is a manifold with some Riemannian metric, and that in particular implies that it is actually a metric space in this sense. And so the name metric is not completely insane. Okay, so another example of important, so the metric tensor is a very important tensor in differential geometry. Another class of important examples of tensors are these things called differential forms. So you already encountered one forms, which are just basically these sort of covector fields, if you want to think about them that way. And in general, you say, okay, well, it's not, I'm not exactly taking a section of a tensor bundle. I'm saying like, oh, well, I have a tensor product in this tangent space. I can define the exterior algebra, right? If you don't like exterior algebras, just think these are alternating tensors, right? So I have, alternating tensors on k copies of the cotangent space at each point. And so what these things do is, yes?
What's an alternating tensor?
Oh, just meaning that, if you have the same thing twice, it's 0. If you swap, if you do some permutation, you change it by a sign of the permutation. So, so I'm just saying, if you have xi1, blah, 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 up to xi, k, well, that's the same as the sine of the permutation times x sigma I1 up to x sigma ik. Yeah. And there's some annoying k factorial factor that I'm not going to worry about. Okay, so, but yeah, so these are things which input a point in the manifold, or at each point in the manifold, you input k tangent vectors, and you spit out a number in an alternating multilinear way. So, think determinant is like an alternating multilinear map. And these are all sort of, in some appropriate sense, these are all determinants. So I guess that's what I just said. At each point, you get an alternating multilinear map on the tangent spaces. Okay. So in R2, what's an example of not a one form, because we already kind of talked about one forms, but like a two form. So it's supposed to be something that eats a pair of vectors and spits out a number. Okay. Well, for example, this thing, right? dx wedge dy. Or if you like to think in sort of bilinear form terms, it's this alternating two tensor, right? On the sphere, there's three different ways to write down exactly the same thing, depending on which coordinate system you like. If you like, rectangular coordinates, which you shouldn't because they suck in this context, you can write it down like this, right? I mean, the surface of the sphere is two-dimensional, and you have three variables here. Like, that's no good. If you like cylindrical coordinates, which you should because they're awesome, it looks like this, right? And if you like spherical coordinates, which are okay, but you get this extra sine theta just because that's what it is. Okay. And so again, what this is saying is like at each point you write down your tangent vector in the sort of the theta z basis, and then you can figure out exactly what the value is supposed to be. So I'm going to not dwell on this slide too much, other than just to say, like, there's a notion of differentiating a form, and what it does is it sort of increases the degree of the form. So you turn a one form into a two form, and a two form into a three form, and so on and so forth. And it's in some appropriate sense, it's sort of like taking the curl of a vector field. This is like a generalized curl. And so curl is awesome in 3 dimensions, but it sucks because it doesn't generalize to higher dimensions. So if you have a vector field in 4 dimensions, like, what do you mean the curl of the vector field? Like, there should still be an appropriate notion. And the answer is, okay, well, you dualize, you don't think about a vector field, you think about a one form, which is some sort of dual object. You take the exterior derivative, and that gives you a two form. And the point is, like, in 3 dimensions, a two form is sort of like a one form because, if you have dx wedge dy, well, that's like dual to dz, and so you can translate between them. But in 4 dimensions, dx wedge dy is like dual to dz wedge dw, which is like still a two form. So you can't really interpret it as a tangent vector. Anyway, there's some not actually that bad formula. You just say, okay, well, look, I can write in local coordinates my form as like some coefficient times one of these sort of standard basis one forms. And then what do? Well, for each index, I just differentiate that coefficient function by that index and then multiply by the corresponding one form, or the differential of that coordinate, really, is the way to think about this, and wedge it with whatever is left. Now, if there's already an xj over here, that's going to cancel because of the alternating this, and this is going to die. So you only pick up the things that you didn't already have. And that's exactly like when you do a curl, right? It's like you only pick up the things that you didn't already have. But the reason I put this down is that once you have forms, you're in the realm of topology, right? You've gone from geometry to topology because now this is a chain complex, or really a cochain complex because it's increasing the degree. You can take the cohomology of the cochain complex, that's something, and then the either amazing or obvious fact, depending on your perspective, is that the cohomology of this thing agrees with the usual singular cohomology of the space with real coefficients. So you don't get torsion out of this. So you've now recovered lots of interesting topological information about your manifold from this sort of very tensorial construction. Okay. And then there's a bunch of stuff about symplectic geometry that I'll maybe skip, just to say that symplectic geometry is awesome. And in particular, if you have a symplectic manifold, you automatically get a measure, and then you can do lots of cool things when you have a measure. But I'm going to skip all that stuff, except to show you the pretty picture. All right. So there's a few things that come up in differential geometry that are not actually tensors, even though they look like tensors because we kind of write them in the same sort of way. So for example, an affine connection is something that comes up all the time. And what this thing basically does is it tells you how to do parallel transport. I won't say more than that other than just say, like, if you have a connection, you have a notion of how to do parallel transport. And in particular, you know how to do these directional derivatives because now you can take your vector field here, your vector field here, you can transport this one over to that one, and then you can do the difference quotient thing, and then you're in business. But what's going on? So it's something that eats pairs of vector fields and spits out a vector field, so it's kind of like a tensorial kind of a thing. And indeed, like, so the way that we write this is that the thing that ended up in the first slot goes in the subscript on this nabla, and the thing that was in the second slot goes here. And the reason for that is because there's an asymmetry, which you've probably already seen if you've been reading ahead. So if I do a linear combination, you know, this is again, this is a C infinity M module, so F1 and F2 are functions. If I do a linear combination in this slot, you just, you know, it's linear in the way that you would like it to be. It's additive in the second slot, like this, but it's a sort of differential operator, so it's not linear in the second slot, it's got a Leibniz rule in the second slot. So it's linear in the first slot, and it's additive with a Leibniz rule in the second slot. So it's not a tensor.
At least with respect to scalars, you see it, right?
Yeah.
Still will be,
Sure. Yeah.
that's useful, right?
Yeah, because, I mean, if F is a constant, then of course, right. Yeah, so yeah, it's agreed. So it's that's a fair point. And then when you have a connection, you have these things called Christoffel symbols, which just say, well, if I have some, you know, basis in xi's, and I do the covariant derivative of xj in the xi direction, I get some linear combination of the x's and the coefficients of these things called Christoffel symbols. And again, they're written in sort of the tensorial kind of a way, but they're not really, they don't transform in a tensorial way, which I don't want to get into, but in some sense boils down to this fact. And then if you have a Riemannian metric, you have sort of like so there's zillions of connections. There's some, you know, infinite dimensional family. Yes?
So an affine connection tells me how to move along one vector field and see how another vector field changes as I move.
Yep, sure, yep. Yeah, that's a good way to think about it. Yep. So if you have a Riemannian metric, so remember the symmetric 0-2 tensor that got me an inner product in each tangent space, there's a unique sort of good connection that's what we call compatible with Riemannian metric and symmetric. So it should satisfy this condition, and it should satisfy this condition. So what is this condition saying? Well, it's saying that, you know, G, you know, it eats vector fields and spits out functions. You know, each vector field is a differential operator, so, you know, I take the derivative of this function, that gives me some new function, and that should be the same as the function where I took sort of the covariant derivative of v in the direction of u and dot product that with w, and then I do it sort of the other way around. These are just definitions. And then you can define this thing called the Riemann curvature tensor, which, if you like, is like a 1-3 tensor field, so you eat a pair of vector fields, and you spit out sort of a linear map from vector fields to vector fields. And what does it do? So if I eat x and y, that's supposed to give me this linear map, so called R of xy. So if you eat z, what do you spit out? You spit out some new vector field, which is this thing, right? And again, kind of forget about this term, because if you have, you know, coordinate fields, this goes away anyway. And what this is telling you is it's sort of telling you like the extent to which these covariant derivatives don't commute with each other. And again, like if you're in a flat space, this is zero, like identically zero as an operator, right? And then, you know, when we talk about, you know, curvature of a Riemannian manifold, often you're talking about like the sectional curvature. So what is this? Well, this is, at a point is, so I take a pair, or I have a two-plane rather, and I take any basis I like for that two-plane, and then what I do is I plug those two vectors into sort of all four slots, so the three slots here, and then I dot product with another one to get a number, right? And then I divide by the area of the parallelogram spanned by u and v. And so this is the number. Yes?
So what would I need to actually work out a value? Christoffel symbols or more information somewhere?
Yeah, if you know the Christoffel symbols, you can work this out. And you know, this looks like a giant, disgusting mess. What's really going on here? Well, if you're talking about a surface, this is just the usual Gauss curvature from, if you ever encountered, you know, Gauss curvature of surfaces. And really what this is doing is, so you're saying at each, you know, what the sectional curvature does is says at a point I choose a two-plane and I spit out a number. So what am I really doing? I'm at a point, I have this two-plane, and what I do is I make a surface which is tangent to the two-plane at that point, and this is just computing the Gaussian curvature of that surface. That's what it is. So it's a direct, in some sense, and in some sense not direct, generalization of Gaussian curvature surfaces. And so, for example, like on any sphere, you know, a round sphere, it's constant. You always get, you know, if you have a sphere radius 1, it's going to be 1 for any point in any two-plane in the tangent space. Okay, and then, well, you have this 1,3 tensor. You can contract it down to a 2 tensor. However you want to talk about this, you take, you know, this is something at each point, each a pair of tangent vectors that spits out a number, so it's like a, you know, a 0, 2 tensor. And so if I plug in a pair of tangent vectors, what am I supposed to get? Well, I get the trace of this linear operator, which, you know, sends any tangent vector to this thing here. Or in index notation, you write it like this. You're contracting out the first and third slots in your tensor, which is the same thing as multiplying by the inverse of the metric tensor after you've turned your 1,3 tensor into a 0, 4 tensor. And then, so this is a tensor. You get a corresponding Ricci curvature, which is just like the value of the quadratic form, the corresponding quadratic form. So this is something that eats a point and a tangent vector and spits out a number. And the interpretation, yeah, I did write this down, is basically you have a point and a tangent vector. You take the average over all two planes containing that tangent vector of the sectional curvature, and that's exactly what this is. And then if you average over, I mean, again, this is like, so this is now a 2 tensor, which I can think of as a 1, 1 tensor. I take the trace of that 1, 1 tensor, I get a scalar. That thing is called the scalar curvature. Another way to think about this is just the average over all tangent vectors at a point of the Ricci curvature, which in turn was some average over all sectional curvatures of planes containing that point. So really, it's an average of sectional curvatures over all two planes in the tangent space at the point. So it's like an average of sectional curvatures. Okay, and then the advertisement for tensor, or one of the advertisements for tensors in physics/differential geometry is it lets you write down equations in very few symbols, right? There's Maxwell's equations, right? I'm not telling you what this Faraday tensor is, but it's not too bad. Likewise for here's Einstein's field equations, right? Okay, this, he had more symbol, right? I mean, if you look up Maxwell's equations in an EM book, you get 4 equations, right?
Why did you use 2 equations?
Just because, why not? Yeah. Okay, so Einstein's field equations, this is the physics, right? Stress energy tensor, which I'm not telling you what it is because I don't understand it, but that's where all the physics is. This is where all the geometry is, right? Ricci tensor, scalar curvature, metric tensor. So geometry is related to physics. That's what Einstein's equations tell you, right? Ricci flow. So if you heard like the proof that Poincare conjecture was using Ricci flow is sort of like, I mean, the Ricci tensor is in some sense like the Laplacian of the metric tensor, and so so the Ricci flow is like sort of like solutions to the heat equation in some rough sense, and so the idea is that like the heat equation sort of uniformizes everything, Ricci flow in some sense kind of uniformizes everything. So on a surface, it's, you know, this is what it looks like. You start with some weirdo surface, and it always sort of simplifies to some nice simple surface. In higher dimensions, you get singularities, which is why the Poincare conjecture was hard, but so it goes. All right, I think I have like 10 minutes left. Cool. So that's sort of as maybe Alexander said, the 15,000-foot view of tensors in differential geometry, which hopefully wasn't too terrifying. but hopefully it wasn't too elementary either. So the last 10 minutes I want to talk briefly about a sort of weird thing where tensors, in some slightly different sense, came up in my life. And so the setting is Grassmannians. So I have a vector space, say n-dimensional vector space, and I'm interested in all d-dimensional linear subspaces of this n-dimensional vector space. So all d-dimensional planes through the origin in my vector space, right? So for example, the Grassmannian of one-dimensional linear subspaces of a vector space is also just projective space over that vector space, right? Here's one of my favorite examples. If I take two-dimensional linear subspaces of R4, a little hard to visualize, right? But it turns out that that space is isometric to a double cover of a product of round two spheres. So it's four-dimensional. That's not too hard to convince yourself of, but it's actually just round S2 cross round S2, where and really I take the quotient where it identifies sort of pairs of antipodal points. So PQ is the same as minus P minus Q, which is kind of cool. Yeah?
What do you mean by a round sphere?
Well, in this case, it's actually a sphere, a standard sphere in R3 of radius 1 over root 2. Yeah. So the idea is you can have topological spheres that are not round, right? They have weird, these things are all topological spheres, right? But they're very much not round. Yeah, so that's all that I mean. All right, now, Grassmannians, of course, go back at least to Grassmann, if not further, right? And there's this very classical construction called the Plucker embedding of the Grassmannian, which, if you're an algebraic geometer, convinces you that the Grassmannian is a projective variety, right? And how does it work? Well, you have a d-dimensional subspace, right? And you choose your favorite basis for that d-dimensional subspace. Doesn't matter which basis you choose. And then you take sort of the k vector, the wedge of all these things. That gives you an element of the dth exterior power of v. And then really well, if I'd chosen a different basis, they would be related by some element of GLD, right? And so I would pay by a factor of the determinant of that element of GLD. And so it's really only defined up to scalar multiplication. So if I take the projective space over that vector space, I get, some projective space. And so now what you're doing is you're saying oh, I've now stuck this thing in here. It turns out to be an embedding. It turns out to be an isometric embedding if you have the appropriate Riemannian metric and so on and so forth. And if you want to write this out a little bit more explicitly, what are you doing? You're saying that, well, I have some preferred basis for V, say if I'm talking in Rn, just the standard basis, and then I get some induced sort of standard basis on the exterior power, which is just all possible wedges of distinct basis vectors with some coefficients. So what are these coefficients? Well, if I think of these u's and just make a tall skinny matrix with the u's as columns, so that's going to be an n by d matrix, I can look at all possible d by d minors and take the determinants, and then that's what these coefficients are. So it's, if you like, it's just sort of a collection of all determinants of d by d minors of sort of the basis matrix for my subspace. And then, the theorem is that if you take the image of this map, that is determined by a system of quadratic equations. What those quadratic equations effectively say is that this wedge is decomposable, so it's not like a sum of two different things, that you can reduce it just as a wedge of a bunch of vectors, not as a linear combination of wedges of vectors. And in this case, where you have two-dimensional subspaces of a four-dimensional vector space, you just get a single equation that looks exactly like this. And so this tells you, okay, this is a smooth projective variety. And now I'm going to play a little sort of a stupid game, and I'm going to turn this wedge back into a tensor at a cost of d factorial. So this is just sort of all possible things, all possible permutations of the indices of the u's, this tensor product summed with a sign of the permutation there. So that's an alternating d tensor. And fine. So if you forget anything about James's talk, you say, I have a giant grid of numbers with these weird asymmetries, right? All right, so this is the Plucker embedding. This is algebraic geometry, but this kind of sucks because this is like n choose d minus 1 dimensional, whereas this was like n times, or d times n minus d dimensional, and n choose d is way the hell bigger than d times n minus d, right? So the people that are interested in applications prefer this choice of coordinate system, where you send a d-dimensional linear subspace to the projection operator, right? So, I have some subspace, there's an orthogonal projection to that subspace, okay? So I can think of this as like a symmetric n by n matrix, and really, since it's symmetric, it's really what, like n times n plus 1 over 2 dimensional, which is a lot smaller than n choose d in general. And this is like a symmetric 1-1 tensor. And now, right, so this is certainly a thing that's true. It's unclear whether it's new or whether anybody but me cares, but I think it's really cool. So you have these Plucker coordinates, you have these projection coordinates, and there's a relationship between them. You can go from the Plucker coordinates to the projection coordinates by effectively squaring this giganto-alternating valence D-tensor. And what I really mean by that is I sort of think of this D-tensor as like a D minus 1, 1 tensor, and then in the other way I think of it as a sort of 1 D minus 1 tensor. I contract out all the crap in the middle, and that gives me a 1, 1 tensor, and up to this factor, which you can easily sort of understand, you get this projection operator. And the proof is basically, the geometry is, well, what does this thing do? Well, I think of it as a sort of an operator. It takes a vector, it projects to u, and then it twists in some appropriate sense. And so when d equals 2, it literally just projects, rotates by 90 degrees. Well, if I do that twice, I've projected and rotated by 180 degrees, and that's why I get a minus sign there. All right, so let me conclude with 4 questions that I have, which may or may not be interesting to anybody, but here they are. So one, there's a notion of flag mean on the Grassmannian, or more generally on flags, which is basically, so I have a bunch of these d-dimensional linear subspaces. I take the sum of the projection operators, that's some n by n matrix, still symmetric, but no longer rank d, and I just take the span of the leading singular vectors. And that's what's called the flag mean. This is a stand-in for the Curvature mean, which is what you really care about, but the Curvature mean is like freaking impossible to compute. So it's very useful. So my question number 1 is like, is there some notion of some kind of singular value decomposition of tensors so that the flag mean also comes from taking the sum of these like Plucker tensor things? And you might say, well, why would I do this when I can do this, which is easy, right? This is like probably incomplete or something, right? And the real answer is because I care about this question. So there's a space called the positive Grassmannian that shows up in string theory and various other places, which is basically, okay, it's the subset of the Grassmannian where all the Plucker coordinates are positive. And then I'm interested in things like, what is the flag mean of that space, right? And it's weird because the flag mean is easy to compute in this projection interpretation, but the condition is in terms of these Plucker, coordinates. And translating between them, okay, in principle I have this sort of formal product, thing, but it's a disgusting, horrible mess, right? So I'd really like to be able to do my flag mean calculation in this setting here. Question number 3, this is like sort of the secant question for the Grassmannian. Let's say I have a linear combination of Plucker coordinates where I don't know these coefficients. Can you tell me what U1 and U2 are? Or even in a more basic question, say I just give you a point in the projective space, can you tell me whether it is of this form or not? And then finally, this is one that occurred to me just over the course of the week, hearing people talk, like, I've thought a lot about Grassmannians. So the sort of the moduli space of all d-dimensional linear subspaces of some vector space. And the geometry of these things is really well understood. They have applications to all kinds of different areas, from signal processing to polymer physics to, you name it. And maybe there's an easy answer to this question, but, the question that occurs to me is like, is there, we have tensor spaces, according to James at least, and you have tensor subspaces, right? What's the moduli space of those things? Does it have interesting geometry? Can you find good coordinates? And would that maybe be helpful in certain settings? So, thanks. Yes?
So when you do have something Grassmannian, do you not also have some kind of group acting there that you can keep track of?
Oh yeah, yeah. So maybe I'll. So the question was like, if you have a Grassmannian, is there some notion of a? Actually, maybe I should do this one so that I don't have to switch. Is there some notion of a group action? Of course, the answer is yes. Like you have your U, in G R D V, right? And then, okay. Depending on who you ask, you should either think of these tall, skinny matrices or short, fat matrices. If you think of them as short, fat matrices, which I've sort of been encouraged to do, you have like a UD action on the left, which sort of does nothing, right? Because you're choosing a different orthonormal basis for the same vector space, right? You also have a big UN action on the right, or in a lot of settings, it's actually, maybe you are interested in some, subgroup of this. So it's, I'm often interested in the subgroup of diagonal unitary matrices acting on the right. And those, send, points in the Grassmannian to different points, but it's still like a symmetry of the space.
So when you have this, does it make sense to talk about sort of a point that's in one of the largest one of these orbits and answer some of these questions since it's generic? Instead of trying to do it for all U1 and U2, for example, the questions we talk about, like what's happening there.
Yeah, sure. Yeah. Yes.
Is that interesting still, or is that like losing?
I think it might be interesting. Because, certainly in any sort of application, if you have sort of stochastic input, you're going to be in the sort of the generic case anyway. And so, yes. Yeah.
Just finish this one. So I think there's a need for some kind of geometry. I don't know, you said isometric at some point.
Yep.
But that's because you got it from R to the D squared or something, and you composed the metric on the subspaces, or how did you get an actual notion beyond just a topology? Where did you get
So the question is, I said something about an isometric embedding somewhere, and the question is like, where did I get a metric on the Grassmannian? Yeah, so where did I get a metric on the Grassmannian? So, right. I'll give you two answers which are really the same answer. So one answer is that I can think of my Grassmannian, I guess, if I talk about a complex, it's all the same thing in some sense, but if I talk about a complex Grassmannian, I can think of this as a homogeneous space in this way. And then the point is that this space up here has a natural Riemannian metric, namely the unique bi-invariant metric. Like this acts on itself from the left and the right. Up to scale, there's a unique metric that is sort of invariant under that action. So this has a natural metric. And so and likewise this and this, and if I just treat this quotient map as an isometric or a Riemannian submersion, then I get an induced metric here. The other way to think about this is like, okay, I have two subspaces, which are kind of hard to draw in sufficiently high dimensions, and you can just say, okay, well look, this unitary group acts transitively on this space, so I can send this subspace to that subspace by some element of the group, right? And what is the shortest path between these two things? Or what's sort of the, sorry, I shouldn't really say shortest path. Take the square root of the sum of the squares of the eigenvalues of the thing that does that, and minimize over all things that do that because there's isotropy. And that's up to some square root of 2 factor, the distance that I'm talking about in the space between these two things. So sort of the size of the minimal rotation that takes this thing to that thing. And if you think about it, that's equivalent to this. Yes.
So a connection you were saying is not a tensor because in that one coordinate it doesn't transform linearly; it's only additive.
Yep.
And then you have this like Lie thing going on.
Yes.
Is it? I mean, it's sort of almost a tensor, right? Like the Lie thing is it's not linear, but it's sort of affine linear. Like it changes by a linear thing, but then plus another term,
Yeah.
right? Is there a theory of things which transform affine linearly rather than linearly, and like, you know, can you sort of generalize this whole thing of tensors to? Is there a body of work around like, okay, sure, Christoffel symbols are not a tensor, but what are they? And
Right. Okay, so the question was, like I said, the covariant derivative was not a tensor because it transforms additively in one of the factors, but you get a Leibniz rule rather than just pulling the coefficient out front. You know, is there some more general sort of context, some generalization of tensor in which, you know, this thing and the Christoffel symbols and various other things would fit into that category, but not, or maybe I shouldn't say category, but into that sort of classification. And I've now repeated your question, but unfortunately the answer is I don't know.
You could use the universal developing algorithm, you get an even bigger monster universe. And it won't say anything different because they're equivalents.
yeah.
Right, right, yeah. And as James pointed out, like, it is a tensor over the reals, over the scalar field. It's just not a tensor over the module of smooth functions. But my guess is there probably is such a theory, but I don't know what it is.